Hello, my name is Dong-un Kang, and I'm a student at Korea University studying civil environmental and architecture engineering. Training handwritten images with GAN and cGAN is the title of today's presentation. I will start by giving you the presentation's order. We will go through what a GAN is in the first chapter. I'd like to discuss the components that make up a GAN first, and then how to train each component individually. I will use a simple dataset to train the GAN and examine the outcomes in the second chapter. I'd like to talk about the constraint of the applied structure and how to improve performance based on the outcomes. To compensate for GAN's weakness, I will quickly introduce the cGAN in the last chapter. In addition, I'd want to wrap up the talk about highlighting the features of cGAN and comparing the results to those of GAN. Let me get right into the point. First, what is GAN? Before I get into GAN, let me explain what machine learning is. Simply described, it is the process of determining its features based on incoming data. This enables us to derive a characteristic probability distribution of data from images, audio waveforms, natural languages, and other sources, and to identify and use a vast amount of data as a result. This machine learning can be divided into two models. The first is the discriminator, which categorizes input data based on the label. We can get the right answer to the questions by using the trained models. For example, if you enter a handwritten image of A into the trained network, the label result 8 is produced. What happens if we reverse this network? It is the generator that reverses the discriminator's processes. When we enter the desired label, this model generates the image. For example, if we enter the label 3 into the network, we can get an image of 3 that looks like we wrote it by hand. The GAN model is one method for training this generator. So, what is the generator's training purpose? I can speak extensively about two goals. The first is that when you enter different input vector, it must generate different images. If you enter A and get a result of 1, like this, you must get a different result, such as 5, when you enter B. The second goal is to prevent unclear, ambiguous images when an image is produced in the generator. Instead, it should be trained to create realistic and plausible images. In other words, instead of the ambiguous 9 images shown on the right, it should generate a clear image result as shown on the left. GAN is a network that combines the two earlier mentioned models. Through the classification function, the discriminator separates the actual input from the generated fake data, and the generator generates the images. At this point, the generator's goal is to generate a plausible image that can be mistaken for actual input data by the discriminator. Through competition, these adversaries try to outdo each other, and as a result, they both train to improve performance. The following is a brief illustration of the training process. The green line represents the generator's data distribution, and the discrete distribution of black represented by each point represents the actual data distribution. At first glance, the two distributions are distinct, and the discriminator can be seen distinguish the differences as shown in the blue line. However, as the training processes, the green line begins to approximate the distribution of the real data, preventing the discriminator from distinguishing between the two distributions. Let's take a closer look at GAN's objective functions and algorithms. On the surface, it appears complicated, but it is simply divided into two parts. The first section trains the discriminator to maximize the value of the objective function. The second part trains the generator in the direction that minimizes the value of the objective function. Now, I will go over each section in detail. First, by organizing the given objective function with terms associated with the discriminator, you can organize it as follows. The first term indicates that the discriminator receives the actual data and trains the one to output. The second term, on the other hand, denotes that the discriminator gets fake data and is tried to output 0. As a result, the overall function value is trained to be maximized. If a given objective function is organized into terms associated with the generator, the first term is no longer required. As a result, the expressions can be organized as follows. The generator will be trained to trick the discriminator into mistaking fake data for real data. This means that the entire function value has been trained to be minimized because the value of D has been trained to be 1. If we divide the algorithm, it can be divided into 3 stages. The first step is to train by entering the actual data into the discriminator. The result must be derived by 1, otherwise the discriminator will be updated by the loss. In step 2, the discriminator is trained through fake images generated by the generator. The result must be 0, and the loss that occurred is used only for the discriminator update. In the last step, the generator is trained. In this case, the purpose is to deceive the discriminator. So the training is carried out with the aim of producing the result value of 1. Now that we've learned about the structure of GAN, so I will explain the process of training handwritten numerical image into GAN and discuss the results. First, I will go over the input data. I used MNIST data which is a handwritten number image ranging from 0 to 9. It includes 60,000 training images and 10,000 testing images. At this point, each image is 28 multiplied 28 pixels in size. The structure of the first GAN used is as follows. The figure below depicts a portion of the structure that was taken, and I used the sigmoid function as an activation function and the mean square error as a loss function. This is because it is a simple form that can be easily applied. The following are the results of the loss values during training and the images generated by the trained generator. First, the upper left graph displays the value of the discriminator's loss during training. The red line represents the value that should converge when properly trained. At first, there is a 0.25 spike indicating that the discriminator and generator are being thought in balance. However, after that, the discriminator outperforms the generator in terms of training performance, and the loss value approaches 0. This can be interpreted as a failure to train properly. The same conclusion can be drawn from the generator loss graph. At the start of the training, you can see that the two models are getting closer to the red line because the training of the two models is working well. However, the loss increases and the value approaches 1. This can be interpreted as a failure to train. The images generated by the trained generator lead to the same conclusion. When 20 images were printed, they were all similar. This means that we cannot output images ranging from 0 to 9, implying that the generator has not been properly trained. So one of the reasons for poor trained outcomes is mode collapse. The generator, which is initially trained through GAN, must produce a variety of results as shown in the left figure. However, when the generator learns the data distribution before the discriminator, generator may reach a point where it produces results that are similar to the real image. This enables the generator to produce only one or few images at that point, a process known as mode collapse. There are numerous ways to overcome this shortcoming. The first approach is to author the activation function. The activation function is a function that takes in an input signal and outputs a new signal. This is used because we do not want to send meaningless signals, but only meaningful signals. When the input signal is large, the slope of the sigmoid function graph is very small. This could cause the slope to vanish during the slope calculation process for weight updates during neural network training. Liquid with a straight line with a fixed slope can be used to address this problem. As the graph shows, the vanish gradient problem can be solved with a constant slope. The second approach is to change the loss function. When the generator produces O and the desired result is T, the loss equation for MSE and BCE as follows. And the two graphs below show the loss function values calculated using the given equation when T is 1. As shown in the graph, BCE will provide more feedbacks to the model for the incorrect answer. In other words, if the generated result is clearly incorrect, the model will be penalized more heavily. The graph of the discriminator loss function is shown below when each method is applied. When BCE was applied, only the size of the value changed, but the shape of the graph remains unchanged. When Likila-Lu is used, the loss value quickly converges to 0, with jumps in the middle. It is difficult to say that it was properly trained because not all of the results converge on the red line. However, when the new method is applied, the loss value exists over a wide range, allowing it to be determined that the result is better than before the improvement. The generator loss graph showed the same result. After applying improving method, the loss value existed over a wide range, which can be determined to produce better results. Furthermore, if you look at the image generated by the generator, you can see that better results were obtained after the improvement. However, there is one regret about the generator that we learned in this manner. I will tell you while watching the video. The image below is a list of images generated by outputting 20 numbers from a trained generator. The results show that each time you create an image, it is different. This means that obtaining the information we require is difficult. So the conditional GAN or cGAN was created to compensate for GAN's shortcoming. cGAN is a model that trains by providing classification information about the generated image by supplementing the existing GAN model with category information. The condition Y has been added to the GAN structure as seen in the structure of cGAN. This enables the generator to train each label's input data and generate data for the desired label. Where condition Y denotes the data type for each class, such as the label or integer data. For handwritten numeric images, for example, the conditions are as follows. When the condition is set to a 10-digit vector image, zero's condition is stored in the form with 1 in the first digit. If we show each condition in this manner, we can list them as follows. The cGAN's discriminator that generated the conditions is trained as follows. The discriminator trains with the correct value if the real image and conditions are correct. If the conditions are different, even if it is a real image, it will train with the incorrect value. Furthermore, regardless of the condition, a fake image will be trained with the incorrect value. So the video below depicts the cGAN training process. I made certain that the number 0 was printed at the top left and the number 9 was printed at the bottom right. As training progresses, it becomes clear that cGAN is training in accordance with the condition. When images generated by trained GAN and cGAN are compared, images generated by GAN are randomly output. On the other hand, the images generated by cGAN are output to meet the specified conditions. We've covered a lot of ground thus far, but I believe there are two key points in this presentation. The first, GAN trains both the discriminator and the generator at the same time, making easier for the generator to train the desired data distribution. The second is that cGAN, which is conditioned to the existing GAN model, makes it a little easier to obtain images that meet the desired conditions. For today's presentation, that is all there is to say. Thank you for taking the time to listen to this length presentation. Thank you.